Vamos a ir con las máquinas de soporte vectorial, que no sé lo que es, SVM. Espero que todo esté bien, audio y todo el rollo. Vamos allá, con nuestro amigo. Hello and welcome.
In this
In this
video,
video.
we will learn a machine learning method called support vector machine, or SVM, which is used for classification. So let's get started. Imagine that you've obtained a data set containing characteristics of thousands of human cell samples extracted from patients who were believed to be at risk of developing cancer. Analysis of the original data showed that many of the characteristics differed significantly between benign and malignant samples. You can use the values of these cell characteristics in samples from other patients to give an early indication of whether a new sample might be benign or malignant. You can use support vector machine, or SVM, as a classifier to train your model to understand patterns within the data that might show benign or malignant cells.
Vale, clasificador, vale, eso, vale.
Once the model has been trained, it can be used to predict your new or unknown cell with rather high accuracy. Now, let me give you a formal definition of SVM. A support vector machine is a supervised algorithm that can classify cases by finding a separator. SVM works by first mapping data to a high-dimensional feature space so that data points can be categorized, even when the data are not otherwise linearly separable. Then, a separator is
Espérate, esto me lo tengo que llevar a los apuntes. Where you are, aquí. Estamos por este punto de aquí, SVM. Vale. Bueno, aunque esto no era aquí exactamente, pero... ¿por qué? A ver si no la armo. SVM. Lo que dice es que es un algoritmo supervisado, ¿vale? Que necesita tener... Supervisado, que necesita tener una respuesta correcta o errónea para él saber si lo está haciendo bien o mal, ¿vale? Hasta ahí, si no recuerdo mal. Y Separator. Vale, funciona con multidimensionales.
estimated for the data. The data should be transformed in such a way that a separator could be drawn as a hyperplane. For example, consider the following figure, which shows the distribution of a small set of cells only based on their unit size and clump thickness. As you can see, the data points fall into two different categories. It represents a linearly non-separable data set. The two categories can be separated with a curve, but not a line. That is, it represents a linearly non-separable data set.
Vale, y la cosa bonita de este... de cómo funciona esto es que puedes separar dos conjuntos de datos de manera no lineal, ¿vale?
Which is the case for most
Que, o sea, hace un dibujo trambólico como este, no necesita hacer una línea recta.
real-world
Vale.
data sets. We can transfer this data to a higher dimensional space, for example, mapping it to a three-dimensional space. After the transformation, the boundary between the two categories can be defined by a hyperplane. As we are now in three-dimensional space, the separator is shown as a plane. This plane can be used to classify new or unknown cases. Therefore, the SVM algorithm outputs an optimal hyperplane that categorizes new examples.
Por lo tanto, el SVM tiene como resultado un hiperplano. Tiene como resultado a un hiperplano óptimo de que categoriza nuevos ejemplos.
Now, there are two challenging questions to consider. First, how do we transfer data in such a way that a separator could be drawn as a hyperplane?
Sí.
And two, how can we find the best or optimized hyperplane separator after transformation? Let's first look at transforming data to see how it works. For the sake of simplicity, imagine that our data set is one-dimensional data. This means we have only one feature X.
Vale.
As you can
Todo
see,
muy sencillo.
it is not linearly separable. So, what can we do here? Well, we can transfer it into a two-dimensional space. For example, you can increase the dimension of data by mapping x into a new space using a function with outputs x and x squared. Now the data is linearly separable.
Vale. Se está inventando cosas y en base a eso hace la separación. Es decir, si tenemos solo un campo, peso, por ejemplo, entonces es lineal. No hay dos dimensiones porque solo hay un valor posible en peso. Es decir, solo hay una línea por la que evoluciona el peso. Lo que hace es, se inventa una dimensión nueva poniendo peso al cuadrado. Así tiene x e y en base a la anterior. O sea, la y es x cuadrado. ¿Vale? Y entonces lo separa en un plano con esto. Y con esto ya puede hacer cosas.
Notice that as we are in a two-dimensional space, the hyperplane is a line dividing a plane into two parts, where each class lays on either side. Now we can use this line to classify new cases. Basically, mapping data into a higher dimensional space is called kerneling.
Vale, entonces crear un espacio dimensional más alto es kerneling. Kerneling. Esto parece interesante. Kerneling. Mapear datos en un espacio dimensional más alto. Vale.
The mathematical function used for the transformation is known as the kernel function and can be of different types, such as linear, polynomial, radial basis function, or RBF, and sigmoid. Each of these functions has its own characteristics, its pros and cons, and its equation. But the good news is that you don't need to know them, as most of them are already implemented in libraries of data
Gracias a Dios está todo implementado ya.
Also, as there's no easy way of knowing which function performs best with any given data set, we usually choose different functions in turn and compare the results. Now we get to another question. Specifically, how do we find the right or optimized separator after transformation? Basically, SVMs are based on the idea of finding a hyperplane that best divides a data set into two classes, as shown here.
Vale,
As
eso
we're in a
me-
two-dimensional space, you can think of the hyperplane as a line that linearly separates the blue points from the red points.
Claro, pero
One reasonable choice as the best hyperplane is the one that represents the largest separation, or margin, between the two classes. So, the goal is to choose a hyperplane with as big a margin as possible.
vale, está
Examples
ahí de acuerdo.
closest to the hyperplane are support vectors. It is intuitive that only support vectors matter for achieving our goal, and thus, other training examples can be ignored. We try to find the hyperplane in such a way that it has the maximum distance to support vectors. Please note that the hyperplane and boundary decision lines have their own equations.
Entonces encontramos un hiperplano que tenga la distancia máxima respecto a los vectores de soporte, es decir, que esté en el medio, de manera elegante. Porque el soporte es como la línea mínima para clasificar, entiendo. Tiene sentido, ¿vale? Sí. La línea debe estar lo más separada de ambas partes posible, punto medio. Y el hiperplano, porque eso puede ser más de 2 dimensiones, puede ser 3 dimensiones, lo que sea.
So, finding the optimized hyperplane can be formalized using an equation which involves quite a bit more math, so I'm not going to go through it here in detail.
Matemáticas a
That
muerte,
said,
ok.
the hyperplane is learned from training data using an optimization procedure that maximizes the margin. And like many other problems, this optimization problem can also be solved by gradient descent, which is out of scope of this video. Therefore,
No me acordaba de este hombre. It's out of scope of this video. Lo voy a usar como meme ya.
output of the algorithm is the values W and B for the line. You can make classifications using this estimated line.
De ello, si me acuerdo, me voy a hacer un corte para cuando alguien me siga en este canal y que diga Hello and welcome con el intro de este señor. Me lo voy a apuntar para hacer la tontería. Es que ya me hace mucha gracia este hombre.
To plug in input values into the line equation. Then you can calculate whether an unknown point is above or below the line. If the equation returns a value greater than 0, then the point belongs to the first class, which is above the line, and vice versa. The two main advantages of support vector machines are that they're accurate in high-dimensional spaces, and
makes
they
sense.
use a subset of training points in the decision function, called support vectors, so it's also memory efficient.
Tiene sentido también.
The disadvantages of support vector
Vale, la ventaja era, una de ellas era obvia, que era lo interesante de hecho que le veía a este método, este algoritmo, que es que funciona en espacios multidimensionales, no solamente en 2 dimensiones como las otras, como una línea, la clasificación típica de líneas o de lo que fuera. Y que, esto no lo había pensado, pero claro, como no usa el conjunto completo de datos, sino los soportes, las líneas de separación de los conjuntos, bueno, líneas o planos, es más eficiente en memoria porque no carga todos los datos a la vez para hacer los cálculos.
Include the fact that the algorithm is prone for overfitting if the number of features is much greater than the number of samples.
Vale, es fácil sobreajustarlo.
SVMs do not directly provide probability estimates, which are desirable in most classification problems.
Vale, otro problema es que no calcula la probabilidad, que es algo que suele interesar en este tipo de problemas.
And finally, SVMs are not very efficient computationally if your data set is very big, such as when you have more than 1,000 rows.
Vale, con un conjunto de datos muy grandes no funciona.
In which situation should I use SVM? Well, SVM is good for image analysis tasks, such as image classification and handwritten digit recognition.
Vale.
Also, SVM is very effective in text mining tasks, particularly due to its effectiveness in dealing with high-dimensional data. For example, it is used for detecting spam, text category assignment, and sentiment analysis. Another application of SVM is in gene expression data classification, again because of its power in high-dimensional data classification. SVM can also be used for other types of machine learning problems, such as regression, outlier detection, and clustering. I'll leave it to you to explore more about these particular
Me lo creo,
problems.
de los ejemplos que
This
son
concludes this
buenos.
video. Thanks for watching.
Thanks for watching. Gracias, señor. No es este señor, ya lo miramos en el otro vídeo. Y ahora vamos a ir con el laboratorio. Que hoy va a ser vamos a hacer todos los laboratorios para el examen, bueno, el laboratorio final. Así que ahora seguimos.